Let us start lecture 7, and the course is phase diagrams in single component and binary systems. So, today we will consider a few topics. We will continue our discussion on concept of equilibrium, because that is the base on which phase diagrams will be drawn, and that the equilibrium concept, equilibrium between different phases, that should be considered for drawing the phase diagrams. Now, in addition to that, we will try to look at a spontaneous process, which is also a natural process, and you will be seeing that the natural processes are all irreversible processes, and during that process we will see that some amount of work will be lost. That is called lost work during spontaneous process, and we will also talk about concept of entropy, and because that is very important, that entropy considerations, and then on that basis we will try to relate entropy with loss of work, as well as it will be related to some of the auxiliary thermodynamic functions like work function, which is denoted as capital A, or gives free energy, which is denoted as capital G. So, let us look at the concept of equilibrium as well as lost work during spontaneous process. If we try to look at what we have done in the last lecture we have seen this equation. Okay. From that we have seen this, and then we have also considered few situations. Situation 1 is when it is isothermal as well as reversible, where we have seen that del Q equal to del W, since del U, which is a state function, becomes 0 under isothermal conditions. And if we have considered that if it is an ideal gas, we can calculate this del W can be calculated as RT ln V2 by V1 for 1 mole of ideal gas. This is condition 1. Second condition, we have taken adiabatic reversible process. There we have seen del U equal to minus del W, this should be in the differential form, du equal to minus del W, where del Q equal to 0, since it is adiabatic, or we can say this is isolated system. That is what we have seen, and in fact when we talk about the internal energy change as well as work form as well as heat form, we can consider we can actually ask one question. That question is, let us say del Q not equal to 0, del W not equal to 0. So, that time if a state change happens, takes place, what will be the work available from the system? This question let us ask. And while asking this question, we can take consideration of reversible as well as irreversible process. Now, we have considered reversible, we have tried to understand reversible form. We saw that a system, if it is going through a reversible change, the system would remain under equilibrium in all those tiny infinitesimal steps and during the process system would feel like that is under rest. So, that is the very concept of reversible. In fact, irreversible is just opposite to that. The system will not be able to feel the equilibrium, rather system would go from one state to another state without realizing how the change is taking place, rather it would realize only the final and initial state. Okay. That means macro state 1 to macro state 2, and that time the process will be spontaneous or natural. So, let us understand this natural process, and then through that mode we will come back to reversible mode again. So, the natural process, if I try to understand, or we can talk about spontaneous process. Okay. Both are same, both are same. Okay. So, in those cases, if a system is left to itself under changing variables, then the system is actually under non-equilibrium. Why? Because we have defined our equilibrium concept as if the system is left to itself under the unchanging defining variables, the system would remain in that condition and it would not change. So, when we consider defining variables, let us say pressure and temperature for a mole of ideal gas, see if we fix pressure and temperature, volume is fixed because of the equation of state, which is RT equal to PV. So, through that equation volume is also fixed. So, that means PVT are fixed. So, the system is defined and that would remain in that PVT state. Now, let us consider one of those variables, let us say temperature. So, temperature is changing, it is not fixed, it is variable. So, if temperature changes, the system or the natural process is like that. If a temperature is high, for example, a system I have taken at a temperature T1, another system I have taken at a temperature T2, and if T2 is at a higher temperature, T2 is higher, T1 is higher than T2, then we would see that the heat would flow from T1 to T2 or system A to system B. So, what is that? So, if I consider a system like system A, this is at T1 temperature, and system B, this is at temperature T2, and if T1 greater than T2, and if the walls of those two system A and B, they are diathermal in nature. So, that means it can actually allow heat to flow in and out. So, then we will see that heat will flow from A to B spontaneously. So, that means the system, if it is at T1 and then if it has to go to T2 at a lower temperature, then it has to lose heat. Okay. So, like that way we could see that a system, if it is left to itself under the influence of changing variable, okay, so the system would keep moving towards another state until unless that changing variable becomes fixed. Okay. So, here temperature, higher temperature, it goes to lower temperature, the heat goes from higher to lower temperature. So, that means that heat flow is spontaneous and during the process, and once the temperature becomes fixed, so another new temperature it would reach. So, the system would again achieve its state of rest. Okay. So, that means it would achieve equilibrium. So, the natural process is also spontaneous, because I could see a heat can spontaneously go from a higher temperature to lower temperature. So, this is basically under non-equilibrium condition, I can write that way. Our system is left to itself, it tries to achieve another state of rest or equilibrium. Fine. And that happens spontaneously. And this actually spontaneous process is actually also called as irreversible process. Why irreversible process? We will come to that. Fine. So, now, so that means system is under non-equilibrium condition, it would achieve equilibrium, and that when it tries to achieve equilibrium, we can also see the direction of change. For example, if T1 is greater than T2, so then heat would flow from A to B. Heat will never flow B to A under spontaneous condition, under left to itself condition. Okay. So, that is spontaneous process or natural process. Now, if I would like to come back, if I like to let us say take heat from T2 to T1, it cannot happen in itself. Okay. So, you have to have external agency to act to take heat from B to A. Okay. That is possible, because there are systems, for example, refrigerator, where you are continuously taking heat from refrigerator to cool it down, and that heat will be released to the environment. Okay. Fine. So, that way refrigerator is cooled. So, that means for that we have to actually act on it, external agencies are acting on it to take the heat. So, that means it is not spontaneously happening, rather we are actually using external agency. So, when that external agency acts to take heat from lower temperature to higher temperature body, that time there will be a permanent effect on that external agency also. Okay. So, that means irreversible process is such, that means nothing can be self activated in case of irreversible process, rather we have to have external agencies or external forces or external energy source to take heat from lower to higher temperature. Okay. So, that is what it is called irreversible process. Similar example can be given. This is, we can talk about temperature effect. So, heat flows spontaneously high to low. Body, and then finally both the system would achieve some temperature which will be in between T1 and T2, and then the system will stay there. So, that means you see that state 1 to state 2, which is final temperature T, once we reach there we can say that the system has reached equilibrium, but in between we do not know what is happening, because only thing we know that heat is flowing from high to lower temperature. Okay. So, that is the information we get from this. Now, we can have a situation like mixing of gases. So, let us say I take two chamber and there is a small hole. This is chamber A, and then another chamber, let us say chamber B, and there is a gas 1, this is gas 2, and both are ideal gas, let us say. So, if we have a stopper there. Now, once let us say this is at temperature T and P, T and P are both constant. Now, once we have that situation, if we remove this stopper, then we will see that both the gases are mixing spontaneously. Okay. But separation of these two gases will not happen spontaneously. So, this is, I would say, these are ideal gases, and mixing is spontaneous. Again, so I could see that the mixing is, the direction of state change is unmixed to mixed. So, that is the state change. Fine. Temperature, pressure both are same, whether you consider state 1 or state 2. But state 1 both gases are unmixed, and state 2 both gases are mixed. And here I am considering ideal gas. If it is real gas, there could be a different situation, will come later. But as of now, ideal gases will mix together and everywhere the composition would be same. Okay. So, it is a kind of homogeneous mixing, and you would also see that the mixing is random. So, that means it is not having any preference. Every gas will try to achieve another gas molecules around it, like that way it mixes randomly and spontaneously. But separating them will not be easy task, somebody has to work from outside to separate them out. So, that means it is also irreversible process. Fine. So, we know that natural process is spontaneous process, and both natural and spontaneous process, they are also irreversible process. They are not reversible process, they are because reversible process, if it is left to itself, it will assume, it will seem like under equilibrium all the way from state 1 to state 2, and that happens under a situation of infinitesimal change from one state to another state. But irreversible process, it can happen suddenly. Okay. But there is a small note here. So, when let us say we have a spontaneous process, as we achieve another set of equilibrium, because we see that under non-equilibrium condition, the system tries to achieve equilibrium, another equilibrium state, and that equilibrium state can be decided by whether it is a immediate there is a rest, or globally there is a rest. Okay. So, there could be a global rest, there could be immediate rest. Immediate rest could be metastable, global rest could be stable state. Okay. So, now when it happens, now as the system approaches equilibrium, so the extent of spontaneity goes down. This is interesting. As the system tries to achieve equilibrium, let us say very close to equilibrium, the spontaneity extent goes down. Okay. So, it decreases. And another interesting fact is, let us say if I consider isolated system. So, isolated system is what? Del q equal to 0, and we know that del u equal to minus del w. Isolated system, because it is surrounded by adiabatic boundary. Now, when we have this, so that means the system possesses some internal energy and the system does some useful work by spending its own internal energy. Okay. Now, that process, if it is spontaneous, gradually the system tendency to do work would reduce, because we have seen that gradually as the system achieves equilibrium, because every system has to achieve equilibrium at the end of its change, spontaneous change. So, when it achieves that equilibrium, gradually the amount of energy available to do useful work, that reduces, that diminishes. Okay. So, at the end we will not get any work. So, finally, at the end of spontaneity, del W should be 0. Okay. So, that means del here it should be, please make a correction, it should be du. Du should be 0. That means I have nothing left in the system which can make itself, no energy is available in the system which can make it available. So, system would have some energy, but there will be no way that energy will be made available for doing extra work or useful work. Okay. So, that means I could see that during the spontaneity or irreversible process, I am losing some bit of work, or the energy which should have converted to work, that energy is not able to convert to work. Okay. So, that means I have some lost work. We can say that. So, starting with, if we start with process, and when it ends with achieving equilibrium, okay, during the process some work is lost, and that work could be either some other energy form or heat energy, like that way. But interestingly, these work will not be available, will not be available. So, I could see that some useful work that the system should have done is not getting done, because that is lost. And this some work is lost, that actually relates to one interesting consideration that is called entropy. Okay. This is a very, very interesting concept. So, where the lost work is converted into entropy. Okay. So, let us look at this entropy term. Fine. Now, when we look at the entropy term, entropy, its correlation with lost work, let us do some experiment. Okay. So, let us take a situation, I have a huge heat container, here it is a kind of reservoir, heat reservoir, and this is isolated. This is isolated. Fine. Now, we have two chamber and chamber is contained with an ideal gas. And let us say the chamber 1 has pressure 1 and chamber 2 or pressure P, chamber 2 pressure is 0 because it is evacuated, and there is a stopper in between. So, I can evacuate this chamber and one chamber I can pressurize, and once it is isolated. So, that means, and this is the temperature T, the bath temperature is T. So, it is, and since it is isolated, so there will be no heat flow. So, now if I open this particular stopper, then we will see the ideal gas will start occupying the other evacuated chamber. So, and if I consider this is volume 1, this is volume 2, the chamber volume. So, I can actually take the consideration of first law, del U equal to Q minus W, or I can take du equal to del Q minus del W. So, now here del Q is 0 since it is isolated, and del W is also 0. Why? Because the gas is expanding under 0 pressure. So, that means if I consider P del V, so P is 0, so that means it should be 0. Okay. So, that means work component is also 0. So, then del U equal to 0. So, that means it is an isothermal process. And this is a spontaneous process also, or irreversible process, isothermal, irreversible, okay. And this is isolated. So, I can say, so this is at a constant temperature, isothermal, irreversible process, and this is in the isolated system. Now, what happens? So, what will be my work done? 0, heat exchange 0. Now, let us say the same process happens under reversible condition. So, if isothermal reversible expansion takes place, then I can calculate. So, that case del equal to 0. So, del q equal to del w. I can write q equal to RT ln. Here the I can say final volume, initial volume. So, I can write RT ln V2 plus V1 by V1. So, I is initial, F is final. Fine. And this is 1 mole of ideal gas. Okay. So, now this should have been my work component. Now, I could see that when I go for a irreversible process and that too isothermal, and pressure the gas is expanding against 0 pressure, the work component is 0. So, that means this part completely is lost. So, for irreversible process, gas expansion against 0 pressure W is completely lost, and the lost work amount is RT ln V1 plus V2 by V1. This is my lost work. Okay. So, that means this is also my Q reversible, and this is also W reversible, because this Q as well as this W both are reversible mode if it is RT ln V1 plus V2 by V1. Once we have that, that means the entire work is lost. Now, I can write Q reversible. So, if I make a relation Q reversible by T, which becomes RT ln V1 plus V2 by V1 divided by T equal to R ln V1 plus V2 by V1. Okay. So, this quantity is nothing but the system. This is I am considering system. So, this quantity is nothing but del S system. Fine. Okay. So, this is the entire system, the isolated system. So, there I could see this is my entropy change, and this entropy change is nothing by Q reversible by T, and we get this amount. So, that means entire work that is lost, that converts to something which is not available for doing work. So, that which is not available. So, that conversion is into entropy term. Okay. I do not know what is the physical essence of entropy, but at least I could see that the entropy change of a system is nothing but the lost work, okay, divided by the temperature of the system. Okay. So, that converts to entropy of the system. Now, if I try to look at the entropy of universe, which is nothing but del S surrounding plus del S system, delta system. So, now what happens to the Q, because it is isolated with the surrounding, the isolated, that Q amount is 0. So, what will be the del S surrounding, since del Q is 0. So, this is 0. So, then it becomes R ln V1 plus V2 by V1. Okay. So, this is a positive quantity or greater than 0. So, that means I could see that when it is an irreversible process, I could see that del S is greater than 0 at least in this situation, or I can say del S universe greater than 0. Okay. So, this particular free expansion, we call it free expansion of ideal gas, and here also this is true, both the cases it is true. So, this is irreversible process. I could see that the lost work is actually converting to entropy of a system, and that entropy is actually decided by the reversible work divided by temperature, provided this is isolated, this is reversible work provided this is isothermal process, remember, provided this is isothermal process. So, or I can say the definition of entropy could be decided by Q reversible by T, or in differential mode del S equal to del Q reversible by T. Okay. So, this is one important definition we can get. So, now we will have to look at this particular del S term more carefully. So, the next lecture what we will do? We will do another experiment, a kind of virtual experiment, and then we will try to look at this entropy consideration and what happens to this entropy when we will reach equilibrium. You will see that an isolated system, when isolated system, if there is a isolated system, the entropy will always increase. Okay? And when the system reaches equilibrium, the entropy would maximize. Okay? So, that very concept we will try to understand in our next lecture. So, till then, thank you very much.